So indeed, this work consists in defining how to implement the previously described model in a continuous environment. So the goal is to allow the implementation on a more complex environment, including robotics implementation. So to test the model, we modify your test environment by making it continuous. So the position of the agent is continuous. The objects have different size. We added two novel interactions that consist in turning left or right of 45 degrees. So the agent quickly misaligns with other objects, and we increase the resolution of the visual system. However, when we tested the model, the signature failed to discriminate, to separate the context into multiple possible contexts. The reason is that we implemented our signature with multiple neurons in competition in order to split the multiple contexts, but in continuous environment, the set of possible contexts is continuous. So it is quite hard to split them in an efficient way. So after some tests, we propose two additional mechanisms in the competition mechanism that are applied when the interaction succeeds. The first rule is applied to the winner neuron in the competition. So the idea is to slightly reduce the absolute value of the weight proportionally to the non-inaction probability of the context on interactions that are not enacted. So, for example, if the neuron has captured this context, but the enacted context looks like this, we'll slightly reduce inactive weight. The second rule is applied to the other neuron in the competition. So we reduce the weight related to active inputs, the enacted interaction, proportionally to the weight of the winner neuron. So if you have the winner neuron that looks like this, we'll remove the weight from the other neuron. So the winner neuron will clean the context that it captures from the other neuron. So I'll show you the evolution of signature in such context. But first, I have to explain what I'm going to show you. So this is how we represent one signature. We have 9 neurons in competition. So each column it's a neuron. We have at the bottom the weight related to primary interaction, and each group here represents a weight related to secondary visual interaction that are related to the same primary interaction, and organized to match their color and ground truth position. It's quite bulky, so instead of representing the whole signature, and as the different rows tend to show similar structure, I will only represent the first row. So at the beginning, we show you an example of interaction related to a static element. We have the signature of bump. So at the beginning, the competition is disabled. So we can see that the neurons start to detect a green object in front of the agent, which is consistent with the property of bump. Then when the result start to become accurate, the competition starts. And you can see that there is one neuron that captures the green element in front of the agent and clean the other neuron. But you can see there is still a kind of green ring around the position. And if you continue the learning, we'll find that this we have the emergence of contexts that has a low probability around the central position. The reason is that there are some pixels in the visual system that are at the edge of the movement of the agent. So this pixel doesn't allow to define if the agent may move or not. So we can see that this new signature can capture this kind of perception aliasing. The most interesting part comes with the signature of interaction related to mobile entities, such as it. So at first, the neuron captures a large blue area, which consists of all the positions from which it is possible to interact with a fish. Then, when the competition starts, we have the one neuron that captures the position in front of the agent and start to clean the other neuron. So the other neuron will share the position around. And through time, we can see the emergence of other contexts that represent the position around the position in front of the agent until all neurons are used. So in fact, and we see that the central is still more probable, but we can see that the other neuron will distribute quite equally the other context, the possible context. So the example shows that the number of contexts that a signature can capture is more important than in discrete environment. We also see similar properties on signature of visual interaction. So it is still possible to project the signature. But when you try to project the signature, we have faced another problem. So we have objects that are represented with multiple interaction, and you can see that the object has the context as an edge made of low weight. The problem is that if we project this whole context, we'll find an image of the object that are quite large in terms of area, but made of low weight. So if the initial context has a high probability, it may remove other projections that may be slightly less probable, but more pertinent in terms of position. So we propose to use the weight as a way to identify how much an interaction will likely to represent the affordance. So we introduce the normalized weight which, on the signature and use both the criteria during the projection, the probability of the context and the normalized weight. So if two projections lead to the same interaction, we use the project between the two as a criteria to define which one will be eliminated, which sequence will be eliminated. And this principle works quite well. We have here an example of projection, of detection, with a static object here that can be sent into space memory as a single entity. And the mobile entity, detected as mobile, as the sequence have a low probability. So here we have everything we need to continue with the subsequent mechanism that I presented just before. So it is so in this work, we show that it's possible to adapt the model with minor change. We also see that the signature can handle perception aliasing, but also that the number of contexts that the signature can capture is more important than the discrete environment. This is why on future work we will try to work on dynamic signature that allow to define dynamically the number of contexts that the signature can handle. Thank you for your attention.
Thank you, Simon. Any question? And it is new talk. One here, and then.
Well, thank you for the really interesting talk. It's interesting to see how your model needed to be modified in order to deal with a continuous space. Mm-hmm. And I'm wondering what kind of modifications you think the model would need in addition to handle more realistic visual input that's also less discrete and being more realistic. So the space is already continuous, but if the visual input's a little bit more continuous.
You mean more complex objects. Well, you have to create a more complex signature model. For example, multiple layer system. So you can handle shape of an object. But the problem with multiple layer neurons is that you lost the explainability of your model. With this, we try to keep the model as simple as possible, so we can still observe the signature through the weight of the neurons. So we can still study how the signature evolve, how we can project them, etc.
If I understand as well, you introduce uncertainty. With going from the discrete to the continuous world, you introduce uncertainty on the position, like on, I think, slide 13, when you have this blur, it's like a probability. You introduce a probability which was not there before in discrete
you mean this probability here? No, it's a probability to that the context will effectively enact the interaction. For example, if you have a blue object in front of you, you will try to enact, but the object has a probability to move. So the interaction will fail. So these are the probability that the agent detect that the context represented here actually enact the interaction.
So this was also the case in the discrete world. These probabilities, this was also the case in the discrete world. This stochastic behavior. The uncertainty, you say here is probability of that it moves. It was also the case in the discrete world or not? In your previous...
well, you have to separate the certainty of an action and the probability of an action. Certainty is that the confidence you have that the context you have in front of you will enact the interaction. The probability is the probability that the context will effectively enact if the context is present. So this is why when you have a static object, the probability will be very high. Around, it will be detected between 90 to 100%.
Okay. Is there any other question? Also, let's thank Simon again for his two talks.